Hello and welcome to Natural Language Processing 0 to NLP. This is a practical and coding focused introduction to modern natural language processing techniques. And today we are on the topic TF-IDF and sentiment analysis. So let's head over to 0to-NLP.com, which is the course website. And you can enroll into the course here and check out the other lessons and assignments here. Now today we are on TF-IDF and sentiment analysis. So that's what I'm going to open up. Here you will find a recording of today's lesson, and you will find a starter notebook that you will use for this assignment. In the starter notebook, click the Run button and then select Run on Colab. So the starter notebook contains some explanations, and then there are code cells which you need to fill out to complete this assignment. And once you fill out and complete this assignment, a copy of your work will be saved into your profile, and you can then take the completed version of your work and make a submission here. So let's go back here into the notebook tab and click Run and select Run on Colab so that we can start executing the code. Now, if you have any questions at any point, please post them here under discussions or post them in the chat. So now this notebook is open for us to use on Google Colab. And now we can start looking at the problem statement. So today we are going to analyze the sentiment of movie reviews from the website Rotten Tomatoes. And we are going to do this by applying the TF-IDF, or the term frequency inverse document frequency technique. And we are going to do this using data from a real-world competition, a Kaggle competition called Sentiment Analysis on Movie Reviews, which we'll look at in just a second. So here's what we'll do today. We will start by downloading and exploring the dataset. We will then implement the TF-IDF technique. We will then train a baseline machine learning model and then make submissions from that model to Kaggle. Then we will train and fine-tune different ML models. So this is something that this is something that you have to do as part of the assignment. Experiment with various ML models and see how good you can get in terms of the score that you get on the Kaggle leaderboard. And finally, you will also be required to add some documentation in terms of the different approaches you've tried and the results you've obtained. And then you can submit your notebook, which is something that we look at towards the end of this lesson. After submitting your notebook, we will review it and we will give you a fail grade with some feedback or a pass grade if you've met all our evaluation criteria. So we've already created sections here, and under each section, we've already created subsections as well. So you simply need to work through this skeleton notebook and fill in the code in the right places. And that's what we're going to do for an example. Now let's open up the dataset. The dataset comes from a Kaggle competition that was held about 8 years ago. And the objective of this competition is to classify the sentiment of sentences from the Rotten Tomatoes dataset. So Rotten Tomatoes is a website where people write reviews about movies and they also give it a rating. Now I'm going to head over directly into the data tab. You can read the description in your own time. But here in the data tab, you will notice that there are 3 files. There is a file called train.csv or train.tsv in this case. The only difference between CSV and TSV is that CSV uses commas for separating numbers and TSV uses tabs. Then you have a test.tsv file and a sample submission.csv file. Now, if you don't see these files here, then you should head over into the rules section and make sure that you've accepted the rules of this competition. Otherwise, you will not be able to view or download the files for this competition. Now, returning to the Data Explorer, this is the data that we would want to download. And then we would want to load it up using pandas. We want to explore it, and then maybe we would want to build a machine learning model. So the train CSV file or the train.tsv file is going to be used to train a machine learning model, a text classification model. And then we have to make some predictions on the test file. and then submit those predictions to Kaggle. And the prediction should have this format, the same format that the file sample submission.csv has. So we'll go through all of that step by step. And we'll go a little faster today because we've already covered this in a lot of detail in our previous tutorial on the back of words. So do check that out if this seems too fast. All right, so the first step is to download the competition dataset. So for this, I am going to copy this command, which is given below the dataset. So I'm going to come back here and I'm going to run this code. Now, of course, this is not Python code. This is a shell command. This has to be run on the terminal. Fortunately, within Jupyter, if we add an exclamation mark, we can run the same command. So now we are going to run this command, and this is going to fetch from the competition sentiment analysis on movie reviews all the data. Now, this requires a Kaggle API key. This will require your login credentials, and you can download your Kaggle API key as a JSON file from your Kaggle account. So let's open up your Kaggle account, and on your Kaggle account, so that is just kaggle.com/me/account, you can scroll down and click on create new API token. And that is going to then download your Kaggle API token, kaggle.json, to wherever you select. And now you can come back into Google Colab or wherever you're running your Jupyter notebook, and you can start uploading that file. Now I'm going to click upload here, and I'm going to upload this file. And remember, every time you run Google Colab, you will have to upload this file. So keep this file around. You don't have to download it again and again, but every time you run Google Colab, you'll have to upload it. All right, one last thing to make it work. You will notice that when I try to run this, it will still not work because we have to also inform the Kaggle command line tool where the config file is present. So that's something we do by setting an environment variable. So I'm going to run import os and os.environ. And now I'm going to set the environment variable. And now I'm going to set the environment variable Kaggle config dir. And I'm going to set it to the current directory. And I believe the current directory, and we can always check the current directory using the pwd command. So the current directory is /content. So I'm going to put it in /content. And let's run it again. So now the Kaggle command line tool was able to read our Kaggle file and then download all the data from the sentiment analysis on movie reviews dataset. Now, of course, this is a zip file. Let's try to unzip this zip file. Once again, we will use a shell command here. All of these things are something that is very easily available to see online. So let's just say unzip and provide the name of the zip file, and let's unzip it into a folder called data. And now you will see a directory here called data, which has the file train.tsv.zip, test.tsv.zip, and sample submission.csv. And this is not a zip file. So let's now just create a few variables so that we can refer to these easily. So we have train fname equals train.csv, data/train.csv, train.tsv.zip. And then we have test fname equals data/train test.tsv.zip. And then we have the sample submission file. I'm just going to call it sub fname data/sample submission.csv without a zip. And now we are ready to start exploring and visualizing the data. So get used to this process of downloading a dataset from Kaggle and then loading it up using a tool like pandas. So let's load up all of these files using the pandas library. So let's say import pandas as PD. And now we can create let's create a raw DF containing all the raw training data. So let's say pd.read.csv. Let's pass it train fname, and let's see if it's able to read this file. Okay, So looks like it was not able to read this file. And the reason is that here it is a .tsv file, and a TSV file simply uses tabs instead of commas to separate values on a row. So there's a very simple fix here. We can just type what is the separator that is used between values in a row. So normally the separator is comma, but we can change that separator to a tab. And now just like that, you can now read a TSV file using pandas. So all these are small tricks that you will pick up automatically. Otherwise you just Google them and learn how to do it. So here is what the data frame looks like. The raw data frame contains a phrase ID. So this is the training.csv file or CSV file. So this is the train.tsv file. It contains a phrase ID. So looks like these are not full movie reviews. Looks like these are phrases picked up from movie reviews. Maybe there were a small section of movie reviews, and from that movie review, several phrases were picked up randomly. So you can see here that it looks like this and this and this and this. All of these are very similar. We can in fact look at some examples of phrases specifically from the column phrase. So raw df.phrase.sample10 .values. Yep. So you can see proceedings is a phrase. That's not exactly a phrase, it's just a word. And then something else is a phrase. And then here, this is half a sentence, some part of a sentence. This is the phrase and this is the phrase. So there are definitely a lot of small phrases here and there. It's not just even a full sentence in most cases. And we have to make predictions on phrases, not even on full sentences or full reviews. So for each phrase, there is an associated sentiment that has been given to us. Probably it has been generated manually, probably automatically, that doesn't matter. But in total, we have about 156,000 phrases from 8,544 sentences. Now, phrase ID and sentence ID are not really useful as data for us. What we are interested in is phrase and sentiment. Let's also maybe load up the test data frame. So that's simply pd.read CSV, test fname, except we want to put a separator here. So the separator is tab. And in the test data frame, we don't have any sentiment. We only have a bunch of phrases. Now finally, let's also look at the submission data frame. So subdf equals pd.read CSV, sub fname. Now the only trouble here is, now in this case, we don't need to provide a separator specifically because there's no TSV here and it's also not a zip file. So that's our submission data frame. So you will notice that the phrase ID 156061, 62, 63 and so on in the test set matches the phrase IDs in the submission data frame. And what we have to do is create an automated system using the training data, which can take the phrases from the test data set, generate predictions for their sentiment, and then replace this submission file. So here all the sentiments are 2 in our sample submission file, and that's not going to obviously give a great result. So we have to replace these values 2s with the predictions of our model, and then we can make a submission to the Kaggle competition using the file that is created by exporting this data frame. In fact, you can also just try submitting the sample submission.csv file and get a basic score, just to make sure that any model that you train is going to be better than the basic score. All right. So that's what we need to do. We have a training set, which we have loaded up in raw.df, which contains phrases and sentiments. Using this, we have to train a text classification model. Now sentiments go from 1 to 5, and you can check this in the data tab here. Sentiments go from, well, looks like sentiments go from 0 to 4. So 0 is negative and 4 is positive. So sentiments go from 0 to 4 and 2 is neutral. So we have to learn to classify phrases into sentiments using the training set. Then we have to look at the phrases in the test set and come up with sentiment predictions for them. And finally, we have to put those predictions into a submission file, and then we can submit that submission file on Kaggle and get a score and see where we might rank on the leaderboard. All right. So now with that out of the way, we might want to do some exploration of the data. Now, since this is an assignment, I will not do much exploration, but here's a quick way to just look at this distribution of the different sentiments within the dataset. So let's say raw.df.sentiment.value counts, and let me normalize those value counts. And let's look at those. So here now we can see that about 50% of these have the sentiment 2, which is neutral. And then 21% have a sentiment good, and 5.8% have a sentiment great. And then about 17.4% have the sentiment bad, and then 0 is just really bad. We can also visualize this. So I can first sort this by the index so that the numbers come up in order. And then I can say plot kind equals bar. And now you see here, you can see that this is a roughly Gaussian distribution, a bell curve, 0 being the negative, the most negative, 2 being neutral, and 4 being the most positive. So this is just one small bit of analysis that we're doing here, but you should do some more analysis, some more visualization, maybe look at more sample data, more sample phrases, explore a bunch of different sentences, and see if the sentiments make sense to you. If not, try to understand why those sentiments have been put in. So it's important to look into the dataset, get a feel of the data before you jump into machine learning. And I encourage you to summarize some insights and learnings from the dataset here. Okay, so now we are ready to implement the TF-IDF technique. Now, the last time we looked at the bag of words technique, and let me just open up bag of words once again. So I'm just going to search bag of words and I'm going to look for images online. So here is how bag of words works. Let's open this image up. So in the bag of words model, we try to take a bunch of text documents. In this case, there are only 3. And then we try to convert them into vectors. And the way we convert them into vectors is first we create a vocabulary of all the distinct words. And sometimes we reduce these words to their root forms using stemming and tokenization and things like that. And then we replace each document with a count of each word in the vocabulary. So the counts 1500200 basically then gives us a vector for this sentence about the bird, bird. So that's the bag of words model. Now another way to approach this, a slightly better way, which accounts for frequency of words within a document and across multiple documents, is the TF-IDF or term frequency inverse document frequency technique. So instead of simply counting the frequency of the word within the document while creating the vector, here's what we do. We first take the term frequency, which means the exact number that we have in bag of words. So we take the term frequency and then we also multiply it with log of the inverse document frequency, which is simply the total number of documents divided by the number of documents containing X. So in this case, for example, the term frequency is 5. So that's fine. That becomes our TF. And the TF is then multiplied with the inverse document frequency. How does the inverse document frequency come up? So the total number of documents is 3. And the number of documents in which the word bird appears is also 3. So 3 by 3 becomes 1. See this formula here, n by df. So 3 by 3 becomes 1 and log of 1 becomes 0. So essentially what this is telling us is since the word bird appears in every single document, it's not really very useful for our analysis and for our machine learning modeling because it's literally present in every single document. So that's something that inverse document frequency accounts for. In this case, on the other hand, the total number of documents is 3, but the number of documents in which about appears is only 2. So the inverse document frequency in this case is going to be 3 by 2 and log of that. Okay, so this is just an adjustment term that accounts for how commonly the word occurs across multiple documents. Now, there are many variations of this TF-IDF model. In many cases, you might see that you add 1 to this value before performing the logarithm so that you don't necessarily get 0 as the result. Another variation is you can divide the term frequency by the size of the document in terms of the number of words it contains. So it could then be a fractional term frequency instead of the absolute term frequency. And all of these are things that you can configure while you're training your TF-IDF model. So I encourage you to look into the documentation of TF-IDF when we look at it. Also, maybe check out a few tutorials on it. And I encourage you to configure the parameters of TF-IDF when you are building the TF-IDF model. All right. So here's what we're going to do. We are going to first learn the vocabulary of the dataset using the TF-IDF vectorizer. And then we're going to transform training and test data. So let's do that. So to learn the vocabulary using TF-IDF, first we need to create a custom tokenizer, which can convert our text into tokens. And also we can add stemming into it, which means we can reduce words to the root form. For example, go, gone, and going can all be reduced to the root form go. So let's try and do that. First, from NLTK dot, actually, I'm just going to look that up. So let's look up NLTK tokenize. So NLTK has this tokenized package. And from the tokenized package, we can use word tokenize to perform tokenization. So from NLTK.tokenize, I'm importing word tokenize. And this is how word tokenize works. You have word tokenize and then you give it a sentence. Let's say something like, is this the real life? And I'm just putting in punctuation just to demonstrate that it breaks up punctuation as well. And looks like we need to also download the punct package within NLTK for this to work. So let's do that, no problem. All right, we're downloading the punct package and now we can use word tokenize here and it turns this sentence, is this the real life, with some punctuations, into a bunch of tokens, including punctuations. So now that we have word tokenize, another thing that we're going to need from NLTK is a stemmer. So I'm just going to rearrange this a little bit. So let's see, NLTK stemming. And once again, here we have documentation. And I'm going to use the snowball stemmer. So from nltk.stem.snowball, import snowball stemmer. Let's import that. Let's run this once again. And let's create a stemmer now. So let's create a stemmer. In the English language. Again, all of this is something we've gone through in a lot of detail in the lesson on bag of words. So do check that out. We'll link to it. And now the stemmer can simply turn words into the root forms. For example, gone becomes go. Okay, gone probably doesn't, but going becomes go, and loving, for example, becomes love. So there's a bunch of stemming that the snowball stemmer can perform for us. So now that we have a stemmer and a tokenizer, we can now define our custom tokenization function. So I'm going to define a function tokenize, which takes some text and then it returns word for word in word tokenize text. Well, actually, we should just call it token here instead of word. That would be more appropriate. So stemmer.stem token for token in words, word tokenized text. So that's our custom tokenization function. And this is where you might want to experiment a little bit, maybe with a different stemmer or maybe with a lemmatizer sometimes. So now let's try tokenizing here and let's try tokenizing the same sentence that we had earlier using our custom tokenizer. Okay, so here's what it does. It is tokenizing the text and then it is also stemming it. So you can see that it is stemming the word fantasy. So fantasy becomes F-A-N-T-A-S-I. Or if I make this really live, you'll see that it is stemming really to R-E-L-L-I. So it's doing a bunch of stemming for us. Now, because we are doing sentiment analysis, all these punctuations may not be very useful for us. So you might even want to remove these punctuations while tokenizing. So here's another thing I'm going to do. I'm going to say for, or I'm going to say if token dot is alpha. Yep. And now this is much nicer because now I just have a bunch of words here. So this is a choice that you can choose to or not choose to make while you are working on the assignment. Now, one thing this is doing is simply reducing the size of our vocabulary because it's taking away a bunch of punctuations. Now, here it is also going to take away numbers. Maybe you might not want that. So you can also just check if it is token.isAlpha or token.isDigit. So I'll let you experiment with that. All right, so now we know how to tokenize our text. Now we can actually go ahead and create a TF-IDF vectorizer. So let's go in here and search for TF-IDF vectorizer. And here it simply says that this is inside the sklearn.featureextraction.txt package. And it can convert a collection of raw documents into a matrix of TF-IDF features, exactly what we discussed. Very similar to bag of words, just a different formula for coming up with the vectors. So let's import from sklearn.featureextraction.txt TF-IDF vectorizer. Okay, and let's create that vectorizer and set some of its parameters. Let's see. So I'm just going to read out the parameters one by one and we are going to start setting them up. Okay, the input, encoding, decode error, etc. are not relevant for us. The lowercase is true by default, so I'm not worried about that. Preprocessor is not applicable for us. Tokenizer, so let us pass a tokenizer. And that's just the tokenize function that we've already created and tested. And it's always important that you test your functions before you pass them into other places to make sure everything is fine so far. One tip about programming is always assume that things are going to go wrong and very defensively test everything that you're doing. Next, we have an analyzer. I don't think we need that. Okay, stop words. Let's bring in some stop words from NLTK. Again, I'm going to search NLTK stop words. And looks like there is some information here. So stop words are simply words that occur very frequently, things like a, and, the, prepositions, pronouns, etc. that may not be very useful for sentiment analysis. So let's see how to get stop words and how to remove those stop words. So if you pass a list of stop words into your vectorizer, it is going to remove those stop words after tokenization. Okay. So first we import NLTK and then from NLTK we have to download stop words. We've already imported NLTK, so I'm just going to download stop words here. All right, so stop words have been downloaded. Next, we can get a list of stop words. So we can say from nltk.corpus import stop words. And then I can say something like English stop words equals stop words dot words English. Now, here is the full list of English stop words. And since this is not printing very well, here's another quick trick. You can always join a list of text or strings using a comma like this, and then it'll print much more nicely. So here is a list of all the stop words. Now, one thing you may want to cut out from all of these stop words is all the negative words. So look here, all the words like no, nor, not, aren't, couldn't, didn't, doesn't, hadn't, because all of these are indicative of sentiment. Now, somebody who is writing a very glowing review will probably not use a lot of these words. They may use a few of them, but not a lot of them. On the other hand, somebody is writing a bad review is definitely going to use some of these. So that's why you may want to use a smaller list of stop words and not this full list of stop words. So let's do that. Let's actually just take a small list of stop words, maybe all the way up till here, where no stop words, where no negative words are included. Now, here's another quick trick I'm going to show you. Now, if I try to type this directly, there's a problem. But here's what I can do. I can say stop words equals, or let me first convert this to a single string, stop words str. Actually, let's do it a different way. So here are all the words that I need, and I'm just going to try and guess here the number of words that I have here. I'm just going to try and guess how many words there are. So I'm guessing here that this is maybe 60 words. No, maybe 80 words. I'm going to keep increasing that number till I get to about the negative words. All right, maybe 120, 150. Okay, 150 is too much. 120 should probably do it. Yeah, maybe under 120. So just a few less, 115. So I'm just going to use the first 115 words. Now you can make this happen in other ways as well, but I'm just using the first 115 words here as a stop words. So my stop words, I'm just calling it selected stop words, equals English stop words 115. All right, so now we have a set of stop words or words that we don't want to keep in our vocabulary. So once again, we have imported the TF-IDF vectorizer, which is going to take a bunch of text and it is going to convert them into vectors using the TF-IDF technique. We have passed it a tokenizer, and I am now going to pass it a list of stop words. And I'm not going to use a full list of stop words. I'm going to simply use the selected stop words that I have created. Contains the first 115 stop words. From the point where negative stop words were present, I've excluded them. Let's see what else we have. Token pattern is not relevant here, but here's one thing that I want to experiment with this time, the n-gram range. Now, when you're creating these vectors, instead of just counting the frequency of every single token separately, you can also count frequencies of two tokens occurring together. For example, things like I am, or maybe romantic comedy. So if you see the two words romantic comedy coming together, that is an indication maybe that this is a description about the movie. Maybe it has something to do with the positive rating. So you can capture groups of two words occurring in sequence by passing n-gram. So you can pass a range of n-gram values. So let's just pass n-gram range. And by default, it has the value 1, 1, which means that it only looks for n-grams with n equals 1. That means it only looks at individual words. But on the other hand, if we pass the range 1, 2, then it is going to count the frequencies of all the individual words. And then it is also going to count the frequencies of two words occurring together in a particular order. Things like romantic comedy or action drama, which may be a phrase used to describe a movie. So you can play with this. Instead of starting with individual words, you can also just start with 2 grams and maybe go up to 3 grams and 4 grams. So that's up to you. Now, n-gram simply means that it's a collection of more than one word in a particular sequence. And we will look at some n-grams when we study the vocabulary. Then max df, min df, I encourage you to check these out. But max features, so I am going to limit my vocabulary to 2000 words. You can try increasing this as well, but in my case, this should do the job. So that's my vectorizer. I don't see any other very useful options here, but I encourage you to check out each one and see what it can do for you. Now that we have a vectorizer, now we need to learn the vocabulary. So we can just say vectorizer.fit and we need to give it the text on which it needs to be fitted. So that's simply raw df dot phrase. This contains a list of all the phrases. Let's fix that. So raw df dot phrase contains a list of all the phrases, and this may take a minute or two to execute because we have over 150,000 phrases. So what it's doing is it's going through every single, first it's tokenizing all the phrases, and it's going through every single unique token that is left after removing stop words, after removing punctuations, after performing stemming. And then it is counting the frequency of every single token. And then it is also looking at two tokens occurring together in sequence, and it is counting the frequency of those as well. So now that this is fitted, we can actually check what is the size of the vocabulary. So let's check by typing len vectorizer dot vocabulary underscore. You can see the vocabulary is 2000 elements, and we can also check the first few elements. So let's check vectorizer dot get feature names out, and let's maybe look at the first 200 words in the vocabulary. So here are the first 200 words in the vocabulary. You'll notice that there are no punctuations here because we have removed the punctuations in our tokenized function. You'll notice that most of the stop words are not present, but you will also notice that the negative stop words which we haven't removed will be present. Now you can see here that there are certain bigrams apart from single words. For example, action movie. So that's a bigram. Adam Sandler. So that may be an indication depending on how Adam Sandler's movies are generally rated. Then we have possibly a few other bigrams that will show up once we try and yeah, better than. So once we big screen, that's another, probably somebody is talking about this is something you should watch on the big screen, and maybe that is a good review. So you can see that bigrams are also very useful because two words occurring in order may convey far more information than each of those words individually. All right, so now we have trained our vectorizer. It knows its vocabulary, and now we can actually convert the inputs that we have. We can convert them. So now we can actually convert the inputs that we have, which is the training set and the test set, into TF-IDF vectors. So let's close this. And quick note before we go into transformation. As soon as you save the page, as soon as you save this notebook, it is going to get saved into your Jovian profile. So you can always go into your Jovian profile and check out your saved work. So now returning here, to transform the training and test data, first we'll transform phrases from the training set. So let's call it inputs. So inputs equals vectorizer dot transform raw df dot phrase, and let's just recall raw df here, what that looks like. So raw df contains all these phrases which are picked from various sentences, and vectorizer dot transform is going to use the vocabulary and apply the TF-IDF formula and convert each of these text documents, each row, into a vector. Let's do that. That is again going to take possibly a few seconds, maybe up to a minute. And once that's done, we will be able to view maybe the shape of the matrix that got created. Maybe we can also look at one of the values. Okay, so you can experiment with a smaller vocabulary size if this takes too long for you. But now that all the inputs have been transformed, so all the phrases have been transformed into inputs, you can see we once again have 156,000 rows within the input. But now instead of having 4 columns, we have 2,000 columns. one column for each word in the vocabulary, or one column for each term in the vocabulary. Now the term could be a single token, the term could be 2 tokens. And let's check out the first row, maybe the first 200 values in the first row. Yes, so here now you can see we've just printed out the first 200 values in the first row. Maybe we can even just print the first 100 and we should be fine. So here we've printed out the first 100 values within the first row of the transformed inputs. And now you can see here that it still contains most zeros. It is a sparse matrix. However, instead of containing numbers, it contains these floating point values. And that's because of the TF-IDF formula. Remember, we multiply with the IDF, which is a logarithm of the total number of documents divided by the number of documents in which the particular term appears. And also you can now compare this with the vocabulary here. So you can go through the vocabulary and see that a series of escapades demonstrating such and such is what it says, demonstrating the adage. So it's possibly the word adage that shows up somewhere here, A-D-A-G-E. Okay, maybe not the word adage, maybe something else. So you can print out the sentence and you can look at these positions within the vector and you can compare them with the vocabulary to verify that wherever you have non-zero values, those words actually do occur in that sentence. Okay, so I'll let you verify that. And it's important to verify that because if you don't do that and there's something wrong with it, you will not discover it until much later and it'll be very difficult to figure it out. So that was converting the training set into vectors. Similarly, we have the test set. I'm going to convert it into test inputs by doing vectorizer.transform testdf.phrase. Now remember again that the vectorizer should be fitted only on the training data, not on the test data, because then it will learn a different vocabulary for the test data. So you fit on the training data, but you transform both the training inputs and the test inputs separately. So now we have test inputs. We can check the shape of test inputs. And we can verify that it has the same number of rows as the test data frame. So the test data frame contains 66,292 rows, and that's the number of rows we obtain. Of course, each of these phrases has been turned to a vector of size 2000. Perfect. Now that we have converted our text documents into TF-IDF vectors, we can now create a simple baseline model and make a submission to Kaggle. So let's start doing that. And the way we'll do that is by first splitting the training and validation sets, then training a logistic regression model, the most basic classification model. Then we will study the predictions on some sample phrases. And finally, we will make some predictions and submit them to Kaggle. Now, before I do that, once again, I'm going to save my notebook. And if I go back to the assignment page and I reload this page, you will see a tab called Your Notebooks, which contains your version of the notebook. So you can see that all the code that I have just typed is present under this notebook, Your Notebook. So every time you run some code from the notebook tab, we create a copy of this notebook and put it under Your Notebooks. And this notebook is also present on your Jovian profile, where you can, which you can visit from here. But under Your Notebooks, you have this copied notebook where we have all the code we have, for example, for TF-IDF, etc. And now you can copy this notebook link if you want. You can open it in a new tab, or you can just run it and you can continue working from where you've left off. So whenever you want to stop your work, just save your work on Colab. It'll get saved to Your Notebooks. Come back into Your Notebooks, run it, and you can continue where you left off. And whenever you're done, you can come into the Submit tab and you can make a submission here as well. That's something we'll look at the end too. So that's the simple workflow that you should be following. Let's see if you have any questions. Okay, I don't see any questions here. Let's see if we have any questions here under discussions. Now, if you have any questions at any point, or if you just want to share where you were able to get to on the Kaggle leaderboard, you can make a post under discussions. Now, returning to the topic at hand, we are now going to train a baseline model and then make a submission on Kaggle. So first, let us split the training and validation sets. So here we have the raw DF, and the raw DF has been turned into inputs, which is a sparse matrix of the same shape or the same number of rows, but 2000 columns. Now here is a tip for you. Do not use a random sample of the data as a validation set. In our previous tutorial, we picked a random sample, but this time there's a problem if you pick a random sample. Remember that the training set is for training your model, and then the validation set is for evaluating your model. The validation set is supposed to give you an idea of how your model will perform on data that it has not seen before. And the problem here is a lot of these phrases are picked from the same sentence. You can see that there are several sentences, there are several phrases here, several rows here, which are all part of the same sentence, and we even have a sentence ID. So if you picked a random sample, it's possible that some part of a phrase that is present in the training set may be present in the validation set as well, or vice versa. In which case, the validation set may be too similar to the training set. Now, ideally, you would want to use this model in the real world on reviews that have not yet been written or are not part of the training set. So to make the validation set more similar to real world data, here's one thing we can do. We have a total of 156,000 rows. So we can probably take the first 110,000 rows of data as the training set, and that would be a certain set of sentences. And then the remaining 46,000 or so rows can become the validation set, and that would be a different set of sentences. You can see here that the sentences are all in order. Okay, so all we're trying to do is make sure that the training set and the validation set do not have data that is too similar. So this is one case where we have phrases picked from the same set of sentences. Another case is time series data, where you may want to make sure that your validation set is in the future compared to your training set. So let's do that. So in this case, here's what we're going to do. I'm going to first set a train size. So let's set a train size, and the train size is going to be 110,000. So this is how you write 110,000. You don't need this underscore, but it just makes it easy to read. And it is still interpreted as a number by Python. And now I can say train inputs equals inputs all the way up to train size, up to the position 110,000, and train targets equals raw df dot sentiment. Remember, raw df has this column sentiment. Again, I'm going to pick all the way up to train size. And now we can check the shape here. So train inputs dot shape and train targets dot shape. So train inputs has 110,000 rows and 2,000 columns, which are all the TF-IDF vectors. And train targets has those corresponding sentiments for those 200,000, for those 110,000 columns, for those 110,000 rows. Now let's also create validation inputs, which is simply the remaining. So here we simply say train size colon and val targets equals val size raw df dot sentiment train size colon. Now, if the syntax doesn't really make sense, then you should take our course on data analysis, or you can also check out our data science bootcamp. But this is simply pandas indexing notation to select the first 110,000 and then everything after the first 110,000 rows. And you can check val inputs dot shape and val targets dot shape. And you can see that each of these is 46,000 plus rows, and the inputs have 2,000 columns. All right, so now we have created a training set and a validation set, and now we're ready to train a logistic regression model. Again, logistic regression is a machine learning technique that is used for classification. So we have a course on machine learning on Jovian, so you can go and check it out. And we also have a data science and machine learning bootcamp where you can learn these and apply some of these techniques in far more depth. So I'm going to import logistic regression. Let's just search for logistic regression sklearn, the scikit-learn library. Okay, so it's part of sklearn.linear model. So I'm just going to come in here and I'm going to say from sklearn.linear model import logistic regression. And then I'm going to create a model. So model equals logistic regression. And now we have to fit the model, or we have to train the model using the training inputs and the train targets. So let's fit the model, model.fit train inputs and train targets. And this can take some time, or depending on the configuration, the hyperparameters that you've tuned, for example, the solver, the number of iterations, it can take less or more time. In my case, looks like it did not really converge. So possibly I may want to increase the number of iterations, check out some hyperparameters. But in any case, I'm sure it must have learned something. So now I can actually make predictions. So now I can take the same training inputs and pass them into my model. And I can try to get some predictions for those inputs. Okay, so now I have my predictions from my model. So if I check out the training targets, so these are the sentiments for the first few rows of the training data. So for the first few rows, the sentiments are 1, 2, 2, 2, and then maybe these are the last few rows. Let's check out the training predictions. In this case, the training predictions are 3, 2, 2, 2 and 0, 0, 2. So clearly they're not matching. They're not even close actually. Well, these two are, but then this one isn't. So the 1 is predicted as a 3. That's definitely off. And one way we can test the accuracy of our predictions is using the accuracy score. So I can say from sklearn.metrics import accuracy score. Let's check the accuracy score of training inputs and training targets. So we pass the training targets and the train predictions. So each target will be compared with the prediction and we'll check the accuracy. It looks like it's a 63.8% accuracy. So now already you can go back into the competition and you can check how the competition is being evaluated. If you go into the evaluation section in overview, and it says competitions submissions are evaluated on classification accuracy, which is the percent of labels that are predicted correctly. So we are getting about 63.8% accuracy on the training set. We might want to check this on the validation set as well. So let's again come up with some validation set predictions. So val_preds equals model.predict val targets val_preds. Okay, val inputs. So we just give it a set of validation inputs and model is going to come up with some predictions. And then you can check the accuracy score of val targets and val_preds. And the accuracy score is 57.9%. So clearly the accuracy on the validation set is not as good as the accuracy on the training set. This is exactly what happens in machine learning, that because your model is trained on the training data, it's generally better there than on validation data, which it has not seen while training. And then in the real world, or in the case of Kaggle on the test set, the performance will be even worse. But generally speaking, your validation set and test set scores should be somewhat close and should change in the same fashion. If your validation score goes up, your test score should go up. Otherwise, your validation set is not very useful. All right. So let's now study some predictions on some sample inputs. So I'm going to create a small sample data frame. Let me call it small df equals raw df dot sample of maybe 20. And let's check out small df. So these are all the phrases that are present in small df. And I'm going to take small df and I am going to convert these phrases into vectors. So let me call it small inputs equals vectorizer dot transform small df dot phrase. And you can see that each of these phrases that are present in small df are now converted into vectors of size 2000. And now I can make some predictions here. So I can say small preds equals model dot predict small inputs. And let's look at small preds. So you can see here that the first two, they are and like Evans. These are both neutral phrases with a sentiment 2. And our model was able to classify them as neutral. But if we check the next couple of them, so we have 3, 3, 3. And specifically here, it looks like here he's now more than ever, etc. So, and then strong directorial stamp. This is definitely a positive review. Highest and the performances, this is also very positive. So there seem to be some of these words appearing that would appear more commonly in a positive review. So all of these are positive reviews. And our model is still classifying some of them as normal reviews. So this is something that you may have to address. And this is something that may be related to the frequency of the different classes. If we go back here into our visualization, you can notice that there is a fair amount of class imbalance. You can see about 50% of the data is number 2, which is neutral, and then 20% roughly are 1 and 3, and then only about 5% are 0 and 4. So if you go into logistic regression, under logistic regression, you actually have this class weight option, and you can try passing class weight equals balanced. What that is going to do is it's going to apply a weight so that all of these get balanced. So essentially, let's say it's going to give the class 2 a weight of 1, but it might give the class 0 and the class 4 a weight of 10, so that their weightage towards the loss and their contribution towards the training becomes 5 times more or 10 times more. Maybe it can give these two the weightage of 2, 2.5. So you can pass class weight equals balanced. I will not do that, but I'll let you attempt that on your own. And then that may help the misclassification that is happening for some of these other classes. And even after balanced, you may still want to tune those values manually. So this is called hyperparameter tuning. And ultimately, it is through some careful manual tuning that you will get the best result. Now, this is why it is so important to look at the predictions on some real data. It's all well and good to look at overall metrics and numbers and then just try to experiment with hyperparameters, but only when you look at a specific example like strong directorial stamp and see that your model is probably not able to capture that specific example properly, and see that that is probably because that class is not very frequently occurring, and you know that because you have explored and visualized the data. Only then will you get the idea that maybe you should add a class weight. So always explore the data, understand the data, and make predictions on some actual examples and reason about why the predictions that are wrong. And that will give you ideas on how to improve your model. Okay, so now with that out of the way, we can make some predictions and submit them to Kaggle. So we have the test data frame here, and we've also converted the test data frame into test inputs. So we've taken all these phrases and turned them into test inputs. So let's make some predictions now. So let's say test preds equals model.predict test inputs. And now we can say test preds.shape, let's just print out test preds and see what that looks like. Okay, so this is an array of 3, 3, 2, 2, so a bunch of numbers from 0 to 4. And we now need to, these are the submissions, or these are the predictions that our model has come up with for all of these phrases. And we now need to create a submission file. So we have this submission file that we loaded up as a data frame. It contains phrase IDs, and these phrase IDs are in the exact same order that they're present in the test data frame. And then it contains this sentiment column, which is all twos here. Now we can simply replace the sentiment column with our test spreads. So I'm going to say sub df dot sentiment equals test spreads. And now you can verify that it actually contains the values that we have put in. So now all those twos have gone away and instead our test spreads have come in. Now I'm going to convert it to a CSV file called submission.csv. And I have to pass this index equals none, because if I don't, then it's going to add an additional column with all these numbers in the submission file, which I don't need. Okay, so a submission file has been created. You will actually find it in the files tab here. And you can look at the first few rows of the submission file. So we can say head submission.csv, and you can see the first 5 rows or so. Okay, so this is what the submission file is looking like. We have a phrase ID, sentiment, and we have for each phrase ID a sentiment from our machine learning model. So let me download the submission.csv file. Let me save this on my desktop. And now I can go back here into the competition, and I can go into late submission. Again, make sure that you've accepted the rules of the competition, otherwise you will not be able to do this. And then I can simply drag and drop this file. So the submission CSV file can be dropped in here, and I can just enter a description: simple logistic regression with TF-IDF. And let's submit that. And Kaggle internally has information about the actual sentiment of the entire test data. So it's going to read your submission file. It's going to compare your submission file with the actual submissions which are hidden for you, the actual sentiments which are hidden for you, and it is going to compute the accuracy score just like we did for our validation set. And based on the accuracy score, it is going to give you scores. So there is a private score and a public score. So the entire test set is also split 50-50 into a private test set and a public test set, which is of importance while the competition is active, not so much once it has ended. But regardless, now that we've made a submission, we can see that our score is 0.60099. Now let's see where that puts us on the leaderboard. So the leaderboard here contains about 861 entries. And let's see where 0.60 is present. So 0.60 would be about here. Yeah, let's check that again. So our best score was 0.600. So maybe we might need to scroll down a little more. Yeah, 0.600. So that would put us about here, which is in around the position 450. Now 450 out of some 860 is not a bad score at all. We are already in the top 50%, and we've done practically nothing. We've just used the TF-IDF vectorizer with a little bit of configuration in terms of the tokenization, in terms of removal of punctuation, in terms of picking the right set of stop words. And then we've simply taken those vectors and put them into a logistic regression model. We haven't even configured the hyperparameters of the logistic regression model. So we're already in a very good place, and there's already a lot of low-hanging fruit for you to experiment. So you can, for example, add class weights, which we talked about. You can set some hyperparameters. You can change the solver. You can increase the number of iterations. So do all of those things and see what kind of a result you're able to come up with, first with just logistic regression. And once you're done with that, you should then try some other models as well. So apart from logistic regression, there are several other different types of models. For example, decision trees, random forest, gradient boosting, naive Bayes. Again, all of these are covered. Well, some of these are covered in our machine learning course, and in our bootcamp, we also go into all of them in a lot more depth. So you can check those out, or you can just look at the documentation and see how to use them. So these are all models for you to try. Now, to get a pass grade in this assignment, you should train and fine tune at least 2 other types of models. So pick any 2 of these at least and try to configure some hyperparameters and try to get a score that's better than our basic logistic regression model. And that itself may not be that easy for you to do. So because even the basic logistic regression model is actually a pretty good model. It has already put us in the top 45%. So anything that you try, you'll have to just try it a little carefully. And here is a couple of optional recommendations. You can also use principal component analysis for dimensionality reduction instead of using the entire 2000 columns of data for training each model, which can take up a lot of memory and can also take a long time. You can reduce the number of dimensions to maybe 100 or 200 using something called principal component analysis. Again, something that is more relevant in a machine learning course, but you can read a basic tutorial about it and try to use it. And another trick you can use is you can maybe use a regression model. So instead of logistic regression, which is a classification model, you can use something like linear regression, which can predict a continuous number, maybe a continuous number somewhere between 0 to 4. And you can round those numbers to integers, and maybe you can also clip them in the range 0 to 4. This should say 0 to 4. So the idea is that because there is a certain order to these classes, 0 being the worst and 5 being the best, instead of classifying separately into these classes and treating them as independent, if you can try to predict maybe a number like 2.5 and then round 2.5 either to 3 or 2.3 can be rounded down to 2, that might actually give you a better result because there is more signal that you are giving to the model through the targets. Instead of just saying there are 5 classes, you're saying that this is a range of numbers and please give me a prediction within this range of numbers after learning from the training set. And then I'm going to round your prediction to the nearest class that is available. Okay. So that is one technique that you can try. I'm sure it is going to give you an improvement because it's definitely conveying more signal to the model. Now, the other thing you should do is you should track your progress in a copy of this experiment tracking spreadsheet. So here we've created a spreadsheet for you, Kaggle competition experiment tracking. And in this spreadsheet, you should put in the information, for example, the date November 15, the idea that you've tried. So right now I've simply tried TF-IDF with logistic regression, and note down the scores that it gave you on each of the sets. Let's see here. So on the training set, the accuracy score was 0.63. I'm just going to copy that score here, 0.6381, put that in here. And 0.5795. I'm going to put that in here as well. The public leaderboard score and the private leaderboard score. So both of these were about 6099. So I'm just going to put those in here as well. And the leaderboard position was about 450. Okay. So next time you try maybe a decision tree, you try a random forest or something else, you should try and track that experiment here. And over the course of a Kaggle competition, you often end up performing hundreds of experiments. So to know which ideas are working, which ideas are not working, it's important to keep your work organized. And often you can then combine the understanding from maybe 4 or 5 different experiments to create your best model, or maybe you can ensemble all the models and stack them together as well. So these are some more advanced techniques. So you can use the link that is given here and you can click File, make a copy, and make a copy in your own Google Drive because you will not be able to edit my copy of this. And in terms of comments here, you can note down ideas of what may be done to improve this. For example, adding class weight and increasing max iterations should improve this. Okay. And then you can maybe note down some more things that you're going to try here, try them on different dates and note down the scores. Okay. Now that we've done that, I will also finally close by maybe showing you one more classifier, the naive based classifier. So let's search naive Bayes classifier sklearn. Okay. So looks like Naive Bayes is a module within sklearn, and you can learn a little bit about it, or maybe you can watch a short tutorial about it on YouTube. But the one that we might want to apply here is called multinomial Naive Bayes, and it is used for text classification most popularly. So I'm going to use multinomial Naive Bayes, and it is present in sklearn.naive Bayes. So let's go back here and let's say our model 1 is Naive Bayes. And let's say from sklearn.naive Bayes import okay, and let's call it, okay, let's copy that name properly. It's just called multinomial NB. And let's call this model 2 or model 1 because that's the title here as well. So model 1 equals multinomial NB. And you can configure some of these parameters. So you can see here that it has something called an alpha. It has something called a fit prior, class prior, things that you'll have to look up. So I'm just going to use this multinomial NB as it is. And then I'm going to say model1.fit, train inputs, train targets. And that's going to fit the model. And now I can say model1.predict, train inputs, and that's going to give me a bunch of predictions. And I'm just going to check the accuracy score here. I don't even need to print out those predictions. So of course, ideally, I should then also maybe explore this model on a small set of values, on a small set of inputs, and manually see where it's going wrong and then configure its parameters. But in any case, I'm checking the accuracy score between the trained targets and the predictions provided by this Naive Bayes model. Okay, so this gives us about 58% accuracy. So that's actually less than our logistic regression. So logistic regression is actually a great model for text classification, it turns out. I would encourage you to check out some of these. Check out some of these parameters. I believe you can play around with the alpha. You can probably try to reduce it or increase it. You don't need to change this. You can try fit prior. You can also add class prior if you have information about the prior probabilities or the prior distributions of classes. For example, you might say something like class prior equals, so I believe the values were, let's say about 0.5 or 0.05, 0.2, 0.5, 0.2, 0.05. Okay. Let's fit that once again. And it's slightly better. So the more you play around with it, the more you learn. So I'm guessing you might get a good result with random forest or possibly with SVM, might be better than logistic regression. And of course, there's a lot of hyperparameter tuning that can be done as well. Now, it's not enough to just check the accuracy score on the training set. You always also have to check the test set. So that's where we are also testing the test set. The validation set. And the validation set here is 0.54. So I would now go in here and I would say Naive Bayes with class priors. This is also on November 15. And that gave me a train score of 0.5881. And a validation score of 0.5453. And I would also make a prediction to the Kaggle competition and note that down as well as the leaderboard position. Now, why do we note both training score and validation score? because this also gives us an indication of overfitting. If your training score is very high but validation score is quite bad, then it's possible that your model is overfitting. So you may then need to regularize the model. For example, for a decision tree, you will get a training score of close to 1, but your validation score will be close to 0 because the decision tree overfits very easily. So all of these concepts are more machine learning related, but as far as NLP goes, the difficult part is converting the text into numbers, and from there, machine learning takes over. So similarly, you can try model 2, model 3, and so on. And whatever is your best model, you can just add some information about it here. You can also include the Kaggle score screenshot. And then once you have done all your coding, you should add documentation and explanations into your notebook. Make sure that you are still maintaining the structure. Make sure that your notebook is presentable. Then clean up any stray code or any comments in your notebook. So make sure that only the code that you want to actually show in a project or in a report that you would want to submit to somebody else, only that code is present. You can still have your experimental or exploratory code, but not code that is not working or comments that don't have any meaning. Then include a screenshot of your best score. So that's a good way to close your notebook. Maybe also talk a little bit about which strategies worked, which strategies did not work. So you should think of your Jupyter notebook as a blog post with code inside it. And finally, save it. And when you save it and you go back and you check your notebooks, all of your code is going to appear here. So you can check here that all of our code is appearing here. So you can then go and you can copy this notebook link and you can come in here and you can make a submission. Now, apart from the notebook link, we are also allowing you to submit an experiment tracking sheet link in case you've tried multiple experiments and you have those across many notebooks. So you can just submit one of the notebooks, the one that you've cleaned up, the one that you've documented well, and then you can include the link to your experiment tracking sheet. This is not compulsory. And then you can click submit. And of course, you have to make sure that this is all your own work. You should acknowledge all the external material and sources that you've used wherever possible. If you've looked up code from Kaggle, you should include that link. If you're using one of our notebooks, you should include those links. And if you copy and just paste somebody else's work directly here, that is an act of intellectual dishonesty, and that will lead to disqualification from the course and possibly from the account. In any case, you make a submission and your submission will show up here in submission history. And we are going to evaluate your submission based on these evaluation criteria. Please read them carefully, and it can take a few days for us to evaluate your submission, but you will see a grade here, and you will also see a tick here at the top of this page indicating that you have completed this particular assignment. So the deadline here is indicated, and based on your batch, you might see a different deadline here. So a quick recap of everything we did today. Today, we were looking at sentiment analysis of movie reviews using the TF-IDF technique. We started by downloading and exploring the dataset from Kaggle, which basically requires uploading a kaggle.json file that we obtained from our Kaggle account page, then setting an environment variable to the location of the kaggle.json file, then using the Kaggle command line tool to download the data, and then finally unzipping that data into a data folder. Then we loaded up the data using the pandas library using pd.read_csv. Because we were dealing with a TSV or tab separated values file here, we had to provide a special separator to read CSV. And this was the data. We had a phrase ID and a sentence ID. So a bunch of phrases taken from the same sentence were all different rows, and each phrase had a sentiment that has been provided for us for the purpose of training. And here were some sample phrases. It's important to get a good look at some sample data to get a feel for the data and see where you can apply your human insight to help your machine learning models. The test data frame contains a sentence ID and phrase ID, but does not contain, and contains a phrase, but does not contain the actual sentiments for those phrases. So you have to train a system, a model, which can make predictions on these phrases. And then you have to create a submission file which contains the phrase ID and the sentiment. And you can simply replace the sentiment column in the sample submission file and then submit it to Kaggle. And we saw that the classes have an unequal distribution. So here we have 0 to 4. There's an unequal distribution between the neutral comments, which are the highest, the neutral reviews, and the phrases that are either positive or negative are smaller in number, and the phrases that are the most extreme are the smallest in number. Something that you might have to account for during modeling. There's also a lot more analysis that you can do with the text data. You can create things like word clouds to identify what are the most common words. And you can then summarize some of your insights, which can help you in the modeling process. So then we implemented the TF-IDF technique, where we not only take the term frequency, which is what we use in the bag of words model, where we take each document and replace it or convert it into a vector containing the frequencies of the different words that occur in the vocabulary. So we not only have that term, the term frequency, we also multiply each element of each vector with the inverse document frequency, which means the number of documents divided by the number of documents in which a particular term appears. So that's how you create the TF-IDF vector. Again, this is something that you should probably work out using pen and paper if you are not able to get a clear understanding, or follow along with a basic tutorial. And then we use the TF-IDF vectorizer class from sklearn. So first we created a custom tokenizer with stemming. So we used the tokenize package and the snowball stemmer. We created a stemmer, and then we created a tokenize function which first tokenizes any given text, and then if the text only contains alphabets, which means we don't want any numbers, punctuations, etc., then we want to stem it and return it. So here, for example, is this the real life or is it fantasy? And even if we had some numbers here, all of the numbers and punctuation would go away and we would just have a bunch of words. Then we also created a list of stop words, but we realized that we probably don't want stop words that are negative. So stop words with negative connotations are useful for sentiment analysis. So we just picked a subset of the stop words containing some of the non-sentiment related stop words only. And then finally, we were able to create the TF-IDF vectorizer, where we passed our custom tokenizer, our custom stop words, and we also passed an n-gram range. So we also wanted to look at not just one token at a time, but a series of 2 tokens occurring together. For example, action movie, Adam Sandler, etc., or best director. Then we limited the vocabulary size to 2000. So there's a lot of scope for experimentation here. Different sets of stop words, different stemming, maybe some kind of lemmatization, and then maybe also experimenting with only using 2 grams, or maybe using 2 grams, 3 grams, 4 grams, or maybe using a bigger vocabulary. Then we learned the vocabulary by passing in all the phrases from our training set, and that gave us the vocabulary. And then we looked at some phrases that were in the vocabulary, and we saw that there are definitely things like action sequence or action film. Those might be indicative more of the sentiment than just a single word. Then we transformed the training and test data. So here we took the raw data frame and then we transformed it using vectorizer, and that gave us a set of inputs, which is vectors of size 2000 for each row in the training set. And we could verify by looking at one of these rows that it actually contains these floating point values, because it's TF-IDF at those positions, which corresponds to the words in the vocabulary that this sentence contains. We did the same for the test set. We generated a bunch of test inputs. Then we trained a baseline model. So we trained, and to train a baseline model, we first split our data into a training set and a validation set. So we decided that because we have a bunch of phrases coming from the same sentence, it might not be a good idea to use a random sample as a validation set, which is why we picked the first 110,000 rows as the training set. That's what we're doing here, picking the first 110,000 rows from the inputs and from the sentiment column. And we picked the next 46,000 or so remaining rows as a validation set. And then we trained a logistic regression model. So we simply imported it, created a logistic regression model, fitted it using the training inputs and training targets. And then we were able to make predictions. Of course, there's a lot of scope for improvement here. We can increase the number of iterations. We can use a different solver. We can pass class weights. And once the model is trained, we can get some predictions out of it. And we compared those predictions to our targets, and we saw that there were definitely differences. And the way to quantify this was using an accuracy score. And the accuracy score was 63.8% versus on the validation set, we had accuracies of only 57.9%. And this is always the case because the validation set contains data that the model has not been trained on. And it's closer to what the model will be doing in the real world. Now, it's also important to look at predictions on individual values. That's where we took just 20 sample phrases and then we looked at their sentiments manually. Then we converted all these phrases into the vectors using vectorizer.transform. And then we pass them into the model. So this is how the model would be used in the real world. A review comes in, we convert that review into a vector, and then we pass that vector into the model. The model gives us a prediction. And here we get back a set of predictions. And then we were able to see that in a lot of cases where it's either a 3 or a 1, our model tends to predict 2. And that might have something to do with the distributions of the different classes. So we may have to deal with that class imbalance somewhere. Then to make predictions and submit to Kaggle, we took the test data set, converted the test. We make some predictions on the test inputs. Remember, we don't have any test targets. And then we took the test predictions and we put them into the submission data frame. And then we saved that as a submission file. And this is what the first few lines of the submission file look like. We then took that submission file and we made a submission here. And then based on that submission, we got a score. And based on that score, we were able to see where we landed on the leaderboard, which is somewhere in the top 50%, which is pretty amazing considering we've spent less than an hour and a half working on the problem. Then we saw that we should try to fine tune and train many different types of ML models. So this is left as the actual exercise to you. You should try decision trees, random forest, gradient boosting, naive Bayes, SVM, tune their hyperparameters, use principal component analysis, compare classification versus regression. And if you use a regression model, make sure to round the predictions down to integers, because if with a regression model, you might get a prediction like 2.5 or 2.7. And you may also get predictions outside of the range. You may get a prediction like -2, or you may get something like 27. So you may also want to clip them to the range 1 to 5. So check out np.round and np.clip. These are a couple of NumPy functions. And then you can track your progress in a copy of this experiment tracking spreadsheet, where for every experiment you try, you should add a small description and note down all the scores. And then you can try all these different models, like we've tried naive Bayes here, but it's up to you which ones you want to try. Finally, you should add some documentation. Just add 1 or 2 lines of explanation wherever you feel there is an explanation required for somebody who might be reading the notebook. Clean up any stray code, any comments. Think of it as a report or a presentation that you are submitting. Include a screenshot of your best score just to indicate how much progress you were able to make in this particular assignment. And then you can save your work. And once you save your work, it will be present under your notebooks. And I quickly want to show you that it will also be present on your Jovian profile. So you can go to jovian.ai, go to notebooks, and the same thing is going to be present here as well. And you can either grab the link from your profile, or you can copy the notebook link from here, and you can go into submit and you can make a submission. And we encourage you to submit your experiment tracking sheet as well, although it is not required. And then you can submit. And if your notebook has the structure provided, it contains the appropriate code for each section. All the cells in your notebook are executed. All the section contains appropriate explanations wherever necessary, and you've trained at least 2 types of ML models apart from the baseline models, and it's not plagiarized, then you will get a pass grade in this lesson, in this assignment. So that was TF-IDF and sentiment analysis. I hope you enjoy working on this assignment, and if you have any questions at any point, please head over to discussions and post your question here, and we will get back to you soon. And of course, you can also just post your best score here and let's see who can get the best score using just TF-IDF, or maybe even apply some other technique. See what other kind of vectorizers are available in sklearn. All right. So that was TF-IDF and sentiment analysis. And this is part of natural language processing 0 to NLP. I hope you enjoyed this tutorial. If you did, please share it with others who might find it helpful. Also, do enroll into the course at 0to-NLP.com, and I'll see you next time. Thank you and have a good day or good night.